1. Metric spaces. Problem 1.2. Stereographic projection. Remark. Remark 1. Let xd be a metric space, and let f be an injective function from x to x. Define a new distance d sub f of xy as d of f of x, f of y, for all x and y in x. We now check that d sub f is a metric on x. Identity of indiscernibles. Since d is a metric, d sub f of xy equals d of f of x, f of y, which is always greater or equal to 0. If d sub f of xy equals 0, then f of x equals f of y. Because f is injective, this implies x equals y. Symmetry. By the symmetry of d sub f of xy equals d of f of x, f of y, which equals d of f of y, f of x. This is d sub f of y x. So d sub f is symmetric. Third, the triangle inequality. By the triangle inequality for d of f of x, f of z is less or equal than d of f of x, f of y, plus d of f of y, f of z. This means that d sub f of xz is less or equal than d sub f of xy plus d sub f of yz. So d sub f satisfies the triangle inequality. Therefore, d sub f is a metric on x. Remark 2. Let xd be a metric space, and let f be a function from the interval from 0 to infinity to itself. Assume that f of t equals 0 if and only if t is 0. Moreover, f is increasing and concave. We define a new distance d sub f of xy to be f of d of xy for all points x and y in x. We now check that d sub f is a metric on x. First, identity of indiscernibles. Since d is a metric, d of xy is always greater or equal to 0. Because f is non-negative and increasing, f of d of xy is also greater or equal to 0. So d sub f of xy equals f of d of xy is always non-negative. Moreover, by assumption, f of t equals 0 if and only if t equals 0. So d sub f of xy equals 0 if and only if f of d of xy equals 0, which holds if and only if d of xy equals 0. Since d is a metric, d of xy equals 0 happens exactly when x equals y. Thus, d sub f of xy equals 0 if and only if x equals y. Second, symmetry. Because d is symmetric, d of xy equals d of yx. Applying f, we get f of d of xy equals f of d of yx. Therefore, d sub f of xy equals f of d of xy equals f of d of yx equals d sub f of yx. So d sub f is symmetric. Third, the triangle inequality. Since d is a metric, for any x, y, z in x, we have d of xz is less or equal than d of xy plus d of yz. Let a be d of xy, and let b be d of yz. The cases where x equals z, or a plus b equals 0, are trivial. So we consider the case where a and b are greater or equal to 0, and a plus b is strictly greater than 0. Then d of xz is between 0 and a plus b. So by the fact that f is increasing, we get f of d of xz is less or equal than f of a plus b. That is, d sub f of xz is less or equal than f of a plus b. Now we use concavity of f. Concavity means the following. for any two numbers x1 and x2 in the domain, and for any number lambda between 0 and 1, f of lambda times x1 plus 1 minus lambda times x2 is greater or equal than lambda times f of x1 plus 1 minus lambda times f of x2. Apply this with x1 equal a plus b, x2 equals 0, and lambda equal a over a plus b. Because a and b are non-negative and a plus b is positive, this lambda is between 0 and 1. We obtain that f of a is greater or equal than a over a plus b times f of a plus b plus b over a plus b times f of 0. Since f of 0 equals 0, this simplifies to f of a greater or equal than a over a plus b times f of a plus b. Similarly, if we choose lambda equal b over a plus b, we get f of b greater or equal than b over a plus b times f of a plus b. Adding these two inequalities gives f of a plus f of b greater or equal than f of a plus b. Putting everything together, we have d sub f of xz equals f of d of xz less or equal than f of a plus b, and f of a plus b is less or equal than f of a plus f of b, which is f of d of xy plus f of d of y, z. So d sub f of xz is less or equal than d sub f of xy plus d sub f of y, z. Thus, d sub f satisfies the triangle inequality. Combining all three properties, we conclude that d sub f is a metric on x. As a concrete example, the function arc